We're on to the detailed study, the materials and their use and structures section. This is the same sort of graph we see every year at the start of these. Just check carefully and just read. It's a stress strain graph. In years gone by, sometimes we've seen a force extension graph. This is a stress strain graph, so okay, we know what to do with that. We've got a whole lot of different materials and they have a cross-sectional area given there. Alright, just note that the stress is in megapascals, the strains by 10 to the minus 3. Which of the following options is the closest to the Young's modulus for steel P? So the Young's modulus, when you're looking at graphs, is the gradient. Or in other words, the stress over strain. And we're looking at material P, so we can look at any point inside this first linear region before it changes, it deviates. So I'm just going to look at this end point here. It's a nice point to look at. So my stress there is 40 by 10 to the omega is 10 to the 6 over my strain 1 by 10 to the minus 3, which gives me 40 divided by 1 is 40 by 10 to the 9, which equals 4 by 10 to the 10. That's answer D. Right, same sort of picture to answer these ones. Which of the following is the best estimate of the mass that could be suspended from a cable of steel P, that same cable, with a cross-sectional area, they've given us the area, at its breaking point. So here's its breaking point here. And they want to know the best estimate of a mass. Well, when a mass is hanging, we usually deal with the force of gravity. So that's, if we can work out the force of gravity, we can work out the mass that can hang off it. And force and area relate in the formula of stress equals force divided by area. So force equals stress times area, if we rearrange it. At the breaking point, that's what stress we want, so that's 50 by 10 to the 6. That's our stress. And times that by area, 4 by 10 to the minus 2. And that gives 2 by 10 to the 6. Then, that's my first step. That's in newtons. So if 2 by 10 to the 6 equals mass times gravity, because that's what the force of gravity equals, then I've got mass equals 2 by 10 to the 6 newtons divided by gravity, which is 2 by 10 to the 6 divided by 10 now. You could have done that in your head. You know, if I had a force of gravity of 800 newtons on me, that means my mass is 80 kg, so divide by 10. That's just the formula that I've worked through for that one. It's not too difficult at all. But anyway, that's 2 by 10 to the 5. And there's that answer there. Alright, a sample of steel S is stretched to a strain of this much, which best gives the strain energy. Now on your formula sheet you'll see strain energy is the area under the graph. Area under graph. Now to this point, 1.5 by 10 to the 3, S to the 10 to the 3 is this here, and we're looking at steel S. So steel S to that point, the area under the graph to that point is a triangle. So you count squares, or I'm just going to do a triangle, half base times height. Half base height, which equals to half times 1.5 by 10 to the minus 3, and my height at that point is 20 megapascals, 20 by 10 to the 6. 20 by 10 to the 6 gives me 1.5 by 10 to the 4, which is this answer. Question 4. Engineers decide that R is the best type of steel for a cable and a crane. The most likely reason is, now you might see a question like this and think, oh my god, we never learned about the best type of steel for a cable and a crane. Well, you don't need to, because this type of question, what they actually give you is they give you one answer that makes sense and 5 answers that are just actually wrong. For example, R is the strongest. Well, if, you know, surely you want a strong material for a steel cable and a crane, I agree, But if you look on the graph, strength is area under graph. Area under graph. So they're saying R is the strongest, R has the biggest area under its graph. Well, I would say that Q has a much bigger area under its graph, okay? Because R only goes to here, and you can work out the area under that. But Q goes all the way to here, and you can work out a bigger area. So as you can see, even though you don't need to know anything about steel cables being used for cranes, this just doesn't make sense. R is not the strongest in the first place. R has the highest Young's modulus. Remember, Young's modulus is the gradient. Let's see if R has the biggest gradient. It doesn't. P has the biggest gradient. So again, they've given us a nonsense claim. R has the greatest strain energy to breaking point. Now, strain energy, is what we've looked at here, is the area under the graph. We already know that's not true. It doesn't have the biggest area under the graph. And R has the greatest range of strain values in this elastic region. Let's just check if that's okay. So here's its elastic region out to here. And they say it has the greatest range of these values for its elastic region. Well, S's elastic region is out to here. That's S. Well, it's bigger than S. Q's elastic region is out to here. It's bigger than Q. And P's elastic region is here. So it's bigger than P. So that is true. R does have the largest elastic regions. Now, I didn't know that's what they were looking for in steel cables for cranes, but I do know that that's a true answer. So that's why that's the answer for that one. Now, question 5 turns out is actually a really, really difficult question. And the reason why it's so difficult is it's got so many steps just to get to the answer. And the first time I did it, I thought, oh, this can't be right because there's so many steps. But I guess every year they've really got to put in one tough one for this section, for the detailed study section, even though they're A, B, C, D, just to separate the men from the boys. Anyway, okay, the cable has the length of this, and a cross-sectional area, yes, and we're looking at cable R again, and we've got a mass on it of 1000 kgs, so we can say that therefore the force on it is 10,000 newtons. Which of the following is the closest to the amount that the cable will stretch? This is on this side. I'm going to do my working backwards. So to work out how much it would stretch, that's my changer now. And the formula that I know relates anything to anything is got change in L, strain equals change in L over L. Right, that's the last thing I need to find out. Okay, because once I've got my strain, I can work out that. So I need to find my strain. I can usually find my strain from the graph. Okay, because here's my strain value here. And to get my strain from the graph, I need to find the stress at that value from the graph. So for example, say they said we're looking at S and a strain of 1.5, here's 1.5 by 10 to the minus 3, then you'd say, well, that's because there's a stress of this amount. Okay? So if you're given the stress, you go across, you can work out the strain. So I get my strain from the graph, but I have to have my stress first, and to get my stress, I need to go force over area. So this is the working, all these steps, but I'm going to do them in reverse order to get to this last thing. Alright, so let's go first one. First one is the mass equals 1000 kgs. So the force, we've got that there, equals 10,000 newtons. Alright, second step. This one here. The stress equals force over area, which equals 10,000, and they've given us the area here, 4 by 10 to the minus 2, which gives me for my stress value 2.5 by 10 to the 5. Alright, let's read that off the graph. 2.5 by 10 to the 5. Now this is, remember, 10 to the 6. It's 10 by 10 to the 6. And so 1 by 10 to the 6 is here. So 2.5 by 10 to the 5 is way in the hell down here. There is no way we're going to be able to read off the graph accurately what the strain value is for that. It's just too small. So we've got a bit of a problem. We can't read off the graph. Damn it. Well, instead of reading off the graph, what we can actually do is we can use the gradient of this guy. So if we can use the gradient, we can get some pretty accurate readings. It's like basically saying what's the equation of the line from here to here. So that's what I'm going to do now. The gradient is always called Young's modulus. Young's modulus. So it's always stress over strain. I can pick any values I want to get the gradient here, so I'm just going to pick these values here, 30 by 10 to the 6 by 10 to the 6 over 1.5 by 10 to the minus 3, and that gives me 2 by 10 to the 10. That's my Young's modulus, or my gradient, and I can use that to actually work out the accurate using this guy, and using this guy I can work out the accurate strain. So same thing before is this formula. I'm just going to rearrange Young's module, put it like that, equals stress over strain. These are the symbols for it. I want to find out this. So I've got rearrange, I get stress over Young's modulus. Now I'm going to use my actual stress value. Okay, so I use the graph here for number 3 to work out what the gradient of the graph, what the equation of the line is. Now that I've got the equation of the line, I can use my actual value for the stress I've got in this situation to work out the actual strain. So I'll have to work out that. Alright, so we've got 2.5 by 10 to the 5. That's from here. And the Young's modulus, which I just worked out, was 2 by 10 to the 10. And that gives me a strain of 1.25 by 10 to the minus 5. Alright, so now I've got my strain. Cool. Now I'm going to use this equation rearranged to find that. So the last step is strain equals change in L over L. So change in L equals strain times L, which equals 1.25 by 10 to the minus 5 times, I got that from there, my L is 20 meters, times 20, which gives 0.12325 meters. Okay, it's the same as what I've got this in. Right, then I've just got to say, because they don't have it in meters, they've got the answer in millimeters or centimeters. Well, if I times that by 1,000, I put it into millimeters, which gives me 0.25 millimeters. What a really, really long question. But like I said, separates the men from the boys. If you go into a question like this, and it's just too much for you, especially in the detailed study section, leave it and come back. Remind yourself, maybe with a little post-it note on the page or something. In fact, that's a really good idea, having a little post-it note on the page to come back to it. But in the end, if you don't know the answer, always guess. Never leave an answer unguessed in the detailed study. Okay? You've got a 25% chance of just getting it right.